Next, we're going to talk about analysis. So analysis has its foundations in calculus, but the idea of it is the study of closeness. Closeness, nearness, limits. So, in high school, we'll deal with some colleges, they deal with real analysis. That is analysis on a real number line. Complex analysis is extension, I wouldn't say extension. It is, you can think of it as two real components. Okay, complex analysis is the analysis on the complex number plane. And what you do with these things, for example, we create the real numbers themselves by defining an equivalence class on the Cauchy sequences of rational numbers. Well, first, integers, they are given. They're actually from set theory. We can say that set theory derives them. Later on, we can actually justify them through set theory. So we create the integers. Then we create, for example, Then from the integers, we create the rational numbers. From the rational numbers, we create the Cauchy sequences of rational numbers. And the limits of the Cauchy sequences, the equivalence classes, we have to prove it's an equivalence class first. Equivalence class has to fulfill symmetry, transitivity, and reflexivity. Cauchy sequences that converge to the same limit with elements in the rationals. They are used. These equivalents. Each class is a real number. So that's how you derive the real numbers. So that's in real analysis. Complex analysis, something along the same lines. And there's also many interesting topics in complex analysis and real analysis. For complex analysis, I recommend Complex Variables and Applications by Churchill. This guy, classic book. Classic. However, this is computation based, I would say. So, now you have real analysis and complex analysis. But there's something called general analysis, which deals with the general metric space. So a metric space is a space that is defined with a metric. So a metric has to fulfill many properties. Some of the key ones are, first, given two objects in the space, if you take the metric, which is the distance function, and you switch it up, for example, d of x comma y, that's equal to d of y comma x. So it has to fulfill the symmetry. D of x comma x, the metric, the distance between itself and itself, has to always equal 0. Also, triangle inequality must always hold. So you get the idea. So given the space, you're given the distance function. You don't know how it's an abstract idea of how distance is measured between objects. There's crazy ones. I've seen the taxicab norm. The regular one in Rn is the Euclidean distance. You have things, for example, in function spaces, you have the metric that I talked about before, 1 over pi, the integral of negative pi to pi, f times g, where f and g are the objects in the space. Well, actually, that's an inner product. No, you can say that's good. You can derive. That's an example of a metric in the function spaces. So, we proved many general results in analysis. We like to deal with compact sets. We like to deal with open sets, closed sets. Well, actually, that's also something that's found in set theory and topology, but we deal with that also. See, in mathematics, there's a lot of overlap. Many fields. And analysis has been a personal favorite of mine. I enjoy it because many of the things, they are unintuitive. Unintuitive things means the proof will probably be based on definition. So that has been easier for me personally. So that is to find things on general analysis. I recommend by Marsden and Hoffman, Elementary Classical Analysis. It's a good book. You should read it. So that's what I like to say about analysis. By the way, this is just brief intro. I cannot go that much into it because I have not studied graduate level or even, I just read it for fun, for college, for undergraduate. So, next thing I'd like to talk about, since we were talking about sets, we can talk about set theory. Set theory is actually one of the most recent topics in mathematics, around the 1900s, 1920s, I believe. It is very recent. So they study abstract objects called sets. And some people, and some things in set theory, it's pretty weird. For example, we can have the set of all people in this room, which is some people. We can have a set of things that converge, or things like that. Some sets don't exist. For example, the set of all ordinal numbers, that's not a set, by definition. Well, not by definition, by proof, you can prove that. There's Russell's paradox that says that it gives an example of a set that cannot exist. I don't remember it exactly, but it's an interesting paradox. It's like saying, assume this is a set. By contradiction, though, it cannot be a set. Because, let's see how it works. All sets, the set of all sets which are elements of themselves. And then there's a set of all sets which are not elements of itself. And you can say something like, if you assume this object is in the set, then it has this property, but that property contradicts the fact that it is a set. It contradicts the property that makes it a set. I don't feel like writing on the board, so I'm on my break. This is colloquial, but you can read up on Russell's paradox. So that's an interesting idea. So there was a few paradoxes in 1920s, like Russell's paradox, and some guy said, named Zermelo, he said, you know what? I'm gonna try to create a bunch of axioms so that these contradictions don't exist. So there is consistency. But Zermelo, he failed to prove consistency of his system. So someone named Frankel ended up fixing most of the things, making it formal using FOL. So also there's something called first order logic. It uses quantifiers, all those things. Any exists, you know that. So that is what it is. So Frankel ended up he ended up working on what we use today for our set theory axioms, the Zermelo-Frankel axioms. And those, for example, use the axiom of comprehension, the axiom of existence, there exists an empty set, the axiom of replacement, the axiom of foundation, the axiom of union things, axiom of power set exists, axiom of did I say existence? Yes, I did. So let's quote. But however, Frankel, now this is a big thing in the set theory, and I'm going to talk about it in the next one.